Hi everyone, today we're going to study derivation of equation of an ellipse with center at HK, major axis is parallel to x-axis. First, let us define ellipse. An ellipse is the set of all points in a plane such that the sum of its distances from two fixed points in the plane is constant. The fixed points are called foci, plural of focus of the ellipse. Here we have 2 points arranged horizontally, and we consider this as the foci of the ellipse. Let us draw now the ellipse. Here we have the ellipse. The line through the foci is sometimes called focal axis. Here is the line, and this is the focal axis. The point on the focal axis, midway between the foci, is the center. Here is the center. The points where the ellipse crosses its focal axis are the vertices. So we have 2 vertices. This is the first vertex, and this is the second. The line segment joining the 2 vertices is called major axis. This line segment in red is the major axis. The line segment through the center, perpendicular to major axis, terminating at the ellipse, is called minor axis. This line segment in green is the minor axis. Now let us define eccentricity. The eccentricity, denoted by E, of a curve tells us the amount of roundness of that curve. Take note that the eccentricity of circle is 0. The eccentricity of parabola is 1. The eccentricity of ellipse is between 0 and 1. And normally, you will see this symbol in the books. E is between 0 and 1. Take note that a small eccentricity indicates that the ellipse tends towards being circular, whereas an eccentricity close to 1 indicates that the ellipse is elongated. Now let us derive the equation of the ellipse with center at HK. The major axis is parallel to x-axis. First, let us draw the x and y axis. Then, major axis parallel to x-axis. The center is at HK. Let us now plot the vertices. The first is denoted by V and the other V prime. We know that the line segment connecting the vertices is called the major axis. We let this length be 2a, and then we can now write the coordinates of the vertices. And these are h plus a, k, and h minus a, k, respectively. Next is the minor axis. The points B and B prime are the endpoints of the minor axis, and we let this length be equal to 2b. By then, we can now write the coordinates of the endpoints of the minor axis. And these are h, comma, k plus b and h, comma, k minus b. Now let us go to the foci. Here is the first focus denoted by F, and this is the second denoted by F prime. The line segment connecting the foci is assigned to be 2C. So the coordinates of the foci are h plus c, comma, k and h minus c, comma, k respectively. Now let us take one point of the ellipse denoted by P, and the coordinates are x, y. This is a moving point that represents all the points of the ellipse. Now, the distance of this P with the first focus added to the distance of the moving point to the second focus is always constant. That is by definition of the ellipse. Now, if the moving point P crosses the vertex, we can deduce that k equals 2a. It means the length of this k is equal to the major axis. Now, we can substitute the 2a to this value k. So here is now our new equation. Now, let us use the distance between 2 points to write the respective distances. First, the FP, and the distance is x minus the h plus c, and this is squared, plus the y minus k, and the quantity is squared, plus the distance f prime and p, and this is the big square root of x minus the h minus c, and this is squared, plus y minus k, and this is also squared, and these are all equal to 2a. Now let us simplify this by putting one radical alone in one side. Let's say the second radical we will transpose on the right side. So from positive, it becomes negative. And from here, we're going to square both sides. The left side, when we square this, the big square root will be cancelled. And this is equal to the square of the right side. So this is the square of 2 terms. It means we expect 3 terms in the final answer. So the left side terms will be like this. Only the radicand comes down. And this is equal to the square of 2a is 4a squared. This is the second term. This is the product of 2a and this big radical multiplied by 2. And the third term is the square of this big radical. So it means to say this is plus, only the radicand comes down here. That big square root is cancelled out. Now let us observe the left side and the right side. There is a common term that we can cancel from both sides. And this is the y minus k, the quantity squared. Let us write again our equation, clearing those cancelled terms. Also, let us simplify this term here and also here. And now, let us square the trinomial. Let us use the special product for the square of trinomial here and also here. So we have now x squared plus h squared plus c squared minus 2hx minus 2cx plus 2ch. For the right side, the first 2 terms are copied down here, expansion of the square of this trinomial is x squared plus h squared plus c squared minus 2hx plus 2cx minus 2ch. And then we can cancel some terms from the left and right side respectively. These are the terms that we cancelled. In the next step, we're going to isolate this big radical on the right side. It means all other terms will be transposed on the left side. Some terms will be combined together. So we have now this equation. Now let us divide the whole equation by 4. So the resulting equation is now like this. To simplify further, let us square both sides again to cancel this big radical. On the left side, this is now again the square of trinomial. That would result to 6 terms like this. And this is equal to the square of the right side is a squared, and the big radical sign is cancelled out. Only the radicand comes down here. In the next step, we're going to simplify this term here. We are removing the grouping symbol of h minus c. So here we go. And from this line, we're going to square this trinomial again. So this is now the resulting product. The next step, this a squared, we're going to distribute to each term inside the grouping symbol. So we have now this equation. Let us observe the left side members and the right side members. There are some terms that we can cancel. Here are the terms that we can cancel. And then let us write again the equation, removing those cancelled terms. Here is now the resulting equation. The next step is we're going to rearrange such that all terms with x, y, and h will be on the right side. This is now the resulting equation. And from here, we can see that some pairs of terms have common factors. On the left side, these two terms have common factor, and that is a square. Look at these first two terms. There is common on them, and that is x squared. And then the third and the fourth terms have common factors also, and that is the negative 2hx. Now look at the fifth and sixth terms. There is a common factor in them, and that is the h squared. So what we will do now is to factor out those common factor. So here we go. In our figure here, we can see that when the moving point touches one endpoint of the minor axis, say this B, we can see a right triangle here. We can deduce also that this hypotenuse here is equal to A. This side here is B, and the side here is equal to C. So we can write the Pythagorean relation as A squared equals B squared plus C squared. We can rearrange this equation into B squared equals A squared minus C squared. Remember that this A squared minus C squared is familiar here in the equation, whereas we can substitute the value B squared for this group also here, here, and here. Substituting that value, we have now A squared B squared equals x squared B squared minus 2 hx b square plus h square b square plus the a square times the square of y minus k. Now look at the first three terms here. There is a common factor, which is the b square. Let us factor out b square, so it would result to like this. Look at this trinomial here. This is a perfect trinomial that we can factor out into the square of x minus h. From here, we're going to divide the equation by a square, b square. And if we do that, it would result to an equation that looks like this. 1 equals the square of x minus h over a square plus the square of y minus k over b square. Let us rearrange the right side and the left side. So here is now the equation of the ellipse with center at hk, and the major axis is parallel to x-axis. Now the latus rectum is here. There are two latera recta in our ellipse. Let us solve for the endpoints of the latus rectum. In the first latus rectum, we're going to substitute the value of h plus c for x. So this equation here, we will write again, and then the x becomes h plus c. We can simplify the numerator here because the h minus h becomes 0. So in here, only c comes down, so we have here c squared. In our Pythagorean relation, we can deduce that c squared equals a squared minus b squared. It means we can change the c squared here into a squared minus b squared. So here we go. And from here, we will distribute the a squared to each term of the numerator. So we have now a squared over a squared minus b squared over a squared. And the other parts of the equation, we will just copy here. We can simplify the a squared over a squared into 1. So here we go. And this constant 1 and the constant 1 on the right side will cancel each other. So what we have now is the negative b squared over a squared plus this fraction here, and all equal to 0. Now let us solve for y. This constant here, we're going to transpose on the right side. So from negative, it becomes positive. So we have now this equation. And then this b squared, we will cross multiply to the numerator of the right side. So we have now the square of y minus k, and this is now b raised to 4 over a squared. Let us simplify this equation by taking the square root of both sides. So we have now y minus k equals plus or minus b squared over a. Solving for y, this negative k, we will transpose on the right side. So we have now y equals k plus or minus b squared over a. It means to say this y value here is the y coordinates of the endpoints of latus rectum. This is the latus rectum. The endpoints have coordinates h plus c, comma, k plus b squared over a. The other endpoint has coordinates h plus c, comma, k minus b squared over a. While the other latus rectum will have the same idea, it means the endpoints are here. The coordinates are h minus c, comma, k plus b square over a, and the other endpoint has coordinates h minus c, comma, k minus b square over a. We can deduce now that the length of latus rectum, denoted by LLR, equals 2b square over a. Now the eccentricity, denoted by E, equals c over a. These are the parts of the ellipse. I hope you learned something from this video. See you again next time.